Hey, today we're going to talk about the free falling objects. This is part 2 of the trajectory motion videos. I will have one more video. This one should be quite short because I will just talk about one aspect of trajectory motion, and that is free falling objects. So when we talk about free falling objects, we are on a planet. In this case, we're going to be on Earth, and when we're on Earth, the acceleration will be rewritten as g, which stands for gravitational constant, which equals negative 9.8 meters per second squared. Now I'm going to continue talking, but at the same time I'm going to pretty quickly write the missing units because they don't have them right here. Meters per second squared. When something is falling or thrown or let go, you always know that your acceleration should always equal negative 9.8 meters per second squared. And that's because you might have a problem that says, oh, okay, so we're going to throw a ball in the air, right? How long until it falls on the ground? Well, you will assume acceleration equals negative 9.8 meters per second squared because you know it was thrown. The only way it's not 9.8 is if we're like on Mars, or if we're on a different planet that has less mass and maybe a bigger radius, which causes the gravitational constant to be less. And we'll talk about that a little bit more. The equations are pretty much valid. The only thing you need to change is where you see an A, there goes a G, which essentially is negative 9.8, unless we're on a different planet. Let's look at this. Mr. S finds out that Manpreet used to be a pretty good friend of mine. We don't talk too much anymore, but that's because he is a dentist or something. No, a pharmacist. Anyways, so he ate my last cookie. I get all angry and take Manpreet to the roof. Pretty dramatic. Roof is 20 meters tall building, and I pretty much ask him how was the cookie because I'm so angry that he ate the cookie. Well, it was a pretty good cookie. And he said, had better. So not only did he eat the cookie, but he didn't even appreciate it. So what I pretty much do is I release his neck, because that's how I was holding him, just like they do in the movies. And the question is, how long until Manpreet's inevitable demise? So let's go ahead and do this problem. Mr. S is right here. I'm on top of the building, and then I let go of Manpreet. He fell down. And the question again was, how long did it take until from the moment I let go until he falls all the way down there? Well, there are certain things you need to know from the very beginning. Whenever something is let go, whenever something is simply released, meaning I do not throw it down, I simply open my hands and then something starts falling due to gravity, my initial velocity will be 0 meters per second. When it comes to position, really depends on how you think of it, but we started here and it went downwards 20 meters. My displacement should be negative 20. And that's because typically we say that going downwards is negative. So displacement is negative 20. So you don't need to do the whole initial final velocity as long as you understand that the displacement is negative 20 meters. So technically you don't need to do all of that stuff. And we know that displacement, and we have gravity. Our acceleration is negative 9.8 meters per second squared. Different from velocity. Velocity is meters per second. Acceleration or gravitational constant is negative 9.8 meters per second squared. Do not confuse this with gravity. This is the gravitational constant, not gravity. So if you look at G, if you look at this guy right here, this is a constant, which is different at different places. So which equation has a displacement, an initial velocity, acceleration, and is looking for time? Time is not given. Time is something we're still looking for. Well, you guessed it. Its displacement equals initial velocity plus 1/2 acceleration times time squared. So let's plug stuff in. We know the displacement is negative 20. So that's supposed to be negative 20. Negative 20 equals our initial velocity. Let's go ahead and put stuff down, which equals 0 times time, which is just 0, plus 1/2, and then the acceleration is negative 9.8, negative 9.8 times squared times t squared. So when we've solved this out, we end up getting negative 20 equals negative 4.8 times t squared. Divide by negative 4.8, and you will receive your answer, at least in t squares. So I'm gonna go ahead and pull up a calculator. Alrighty, so when you do calculate it out, you do get 20 divided by 4.8. You do have a negative over negative, that should be positive, which ends up giving you 4.16 repeating, and you're supposed to take the square root of that number. So let's go ahead and square root it, which will give you, let's go ahead and just make it to the 1/2 power, that's the same thing, which gives you 2.0416. Alrighty, so 2.04. That should be the answer for T. You will see a bunch of stuff that's actually incorrect because I used the negative 10. So just go ahead and ignore this. Do not write this down. You can go ahead and look at this and see that if I would have used the correct displacement, that I could have potentially gotten the right answer. But what are you gonna do? And significant figures, I only have one significant figure here, so you should just say 2 seconds. So you don't need all of that stuff. So the answer here is 2 seconds. If you want to use this equation, make sure that's a 20, negative 20, and then you're taking a t squared equaling 4.16 repeating, which was supposed to give you, with correct significant figures, 2. Alrighty, so that is it for this video. I will do another video where I do all of these homework problems just like I did before, and you guys enjoy your day. Bye.